Nth Fibonacci number. The purpose of this lecture is to clarify on the best approach possible for finding the nth Fibonacci number. In the last few lectures, when we were learning about dynamic programming, we kept using this Fibonacci number problem as a prime example for explaining dynamic programming. So automatically you will be of the mindset that whenever you see nth Fibonacci number problem, dynamic programming is the first choice way to go. But this is wrong. There are easier approaches and more efficient approaches that are there for nth Fibonacci number problem. The reason why we used this particular problem as an example for explaining dynamic programming is that this is a very basic problem which makes explanations on dynamic programming much easier. So this does not mean dynamic programming is the best approach for this problem. So here in this lecture, let us see which are the best approaches for solving nth Fibonacci number problem. So whatever we learned in dynamic programming lectures, all those things hold, but the purpose was more about teaching you dynamic programming. So teaching the dynamic programming concept was more on focus. Here we are focusing on solving the nth Fibonacci number problem. Okay. So first of all, what is the problem here? You want to find the nth Fibonacci number. What is Fibonacci series? It starts with 0, then 1. After this, every next Fibonacci number is the sum of previous two Fibonacci numbers. That is, if you want to find the next Fibonacci number, you will take a sum of previous two, 0 plus 1, which is 1. How do you find the next Fibonacci number? 1 plus 1 is 2. Which is the next one? 1 plus 2 is 3. Next one? 2 plus 3 is 5. And so on. So this is how Fibonacci series grows up. The first Fibonacci number, f of 0, is fixed as 0. And next one is fixed as 1. These are the first two Fibonacci numbers. Whatever we learned in the last few lectures, first of all, we learned a recursive approach for solving this problem. So in the recursive approach, what was the problem? We had a time complexity of order of 2 power n, that is exponential time complexity, which is not feasible in practical situations. So what is the second approach that we learned about? We learned about dynamic programming approach. We solved it using memoization and then using tabulation. What is the time complexity that we found? Time complexity we had was order of n. And what about the space complexity? Space complexity was also order of n. Why was this order of n? Because either be it memoization or tabulation, you stored the results for n steps, and that is why space complexity is order of n. Coming to the best approach possible for solving this nth Fibonacci number problem, we will see few approaches. Among them, let us first try to decrease space complexity from order of n to order of 1, and then we will see how we can decrease time complexity as well. That is, even from order of n, we can take it down. The time complexity can be taken down. So let us see how exactly this is done. So the first approach, we are going to decrease space complexity from order of n to order of 1. Let us first see what we have done in case of dynamic programming, where it is consuming space, and how are we going to reduce the space that is used. Let us say you want to find Fibonacci of n. What is the approach that we had used in case of dynamic programming? Let us say we'll use tabulation here. So initially you will create a table. The table is of size, let us say n plus 1. This is the size of your table. What will you do next? You will initialize the first element. So here table is an array only. Okay. T of 0 will be 0. Then you will say T of 1, that is the first element is 1. Second element is 1. After this, you will start a loop. That is for I is equal to 2 to n. What will you do 2 to n? T of I is equal to T of I minus 1 plus T of I minus 2. That is, whatever be the sum of previous two elements, that will be the next Fibonacci number. Whenever you reach t of n, you can return t of n. So this is how you will find the Fibonacci series. How will this work? You will have a table. So here table is an array, okay? In this array, you will have different elements. Let us say 0, 1, 2, 3, 4, 5 and so on. So t of 0, this is defined as 0. T of 1 is defined as 1. After this, how will you fill all these? You will see whatever is the sum of previous two elements, that will be the entry in each of those boxes. So let us say here it is 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5 and so on. So this is how you are going to fill up, and this is how you will find the Fibonacci series. Then here this table or the array is taking up order of n space. How can you decrease this? You actually don't want this complete array to be stored all the time. Instead, you just need to keep track of the previous two elements. So why should you store the whole array and waste your space? Instead, you can just keep track of the last two elements in two separate variables, and using this method, you can directly take the space down from order of n to order of 1. So let us see how this is done. In order to do this, you have to make a very small change. That is, let us say we are not using this table at all. We are not going to use table this time. Instead, we'll simply use two variables. So you can say if the value of n is less than or equal to 1, then you can simply return n. Why is this? Because the 0th Fibonacci number is 0 and the first Fibonacci number is 1. So if it is less than or equal to 1, if it is 0 or 1, then you can simply return that number itself, because that itself is the Fibonacci number. What is the next thing? Instead of having a new table, we'll have two variables to store the previous two elements. Let us say P1 will give you the previous element. Let us say it is 1, and we'll have P2 is the element even previous to that. We'll make it 0. This is how we'll start. After this, what will you do in the loop? Let us say for I is equal to 2 to n. What will you keep doing? In this loop, you just have to sum up both the previous elements in order to find the current element, and then you have to update the previous values. So let us say your current value is equal to P1 plus P2. The sum of previous two elements is your current value. After this, you should update the previous elements. That is, your P2 will become P1, and what is the other change? Your P1 should be updated as your current element. So for the next loop, your P1 and P2 will be updated. And whenever your loop completes, you can return. What should you return here? In this case, you should be returning P1, right? P1 is what will give you the nth Fibonacci number. If you are looking for number 2, if you put 2 here, one time the loop will run. So at the end, you will be updating P1 with whatever is the current at that point. So P1 will automatically hold it. So this is how you can solve the same problem of Fibonacci numbers which we used in dynamic programming. In dynamic programming, it took time complexity order of n and space complexity order of n. This time what did you do? It is still taking time complexity order of n because it is looping through each entry till n. But space complexity, we are no more using the table, because of which space complexity has come down from order of n to order of 1. Then the question is this approach also a dynamic programming approach, or is it not? And the answer is, this is by going by the strict definition of dynamic programming. This is not dynamic programming. This is just usage of two variables, because strictly if you go by dynamic programming definition, you have to use memoization or tabulation for storage. Storage is the core part of dynamic programming. That is, whenever you are having repeated subproblems, you will be storing the values so that you don't have to compute it repeatedly. Without storage, you can't actually call it dynamic programming. But whatever is the idea used here, The logic is inspired from dynamic programming. So you can say this is maybe a kind of space optimized dynamic programming, or you can say this is not dynamic programming. This is a different approach, right? So this you can call as a different approach only, where you are using two variables. The next question is, can you do even better? Instead of order of n time and order of one space, can you do even better in case of time complexity? Let us see what approach should we use so that our time complexity can also be improved. So this is our next task. We are going to improve on the time complexity of nth Fibonacci number algorithm. So for this, we'll be using matrices here. So you don't need in-depth knowledge of matrices. Even if you have basic idea of matrices, that should be good enough. What we are going to do is, we are going to take time complexity from order of n to order of log n. This is what we are going to do by making use of matrices. What we'll do, initially, we'll understand how this Fibonacci series is working. We know f of n, Fibonacci number, nth Fibonacci number is equal to fn minus 1 plus fn minus 2. This is how Fibonacci series works. If we write this in matrix form, how can we write it? This is the first question. The way to express this is, you can write as fn minus 1. So I'm going to write this as in a form of two matrices. I'm going to write this as a matrix multiplication. How will I write this? I'll write it as 1, 1, 0, 1, and then this multiplied with fn minus 1, fn minus 2. So if you see, if you do this matrix multiplication, you are going to get this. So instead of writing this formula, this can be expressed using matrices as this. So this matrix multiplied by this matrix will give you this matrix. So this is how you can express nth Fibonacci number with the use of matrices. Let us refine this a bit more so that we can make an algorithm out of this. So instead of writing like this, is the another way of writing this. We don't know what exactly is fn minus 1 and fn minus 2. What we know is f0, f1. These are the only things that we directly know. Whatever be the other values, we have to calculate it. We know that f0 is 0 and f1 is equal to 1. These are the only two Fibonacci numbers which we directly know. This is always this. The remaining Fibonacci numbers we have to calculate. So we have to eliminate this fn minus 1 and fn minus 2 from here and replace it with f0 and f1. Then only this algorithm can be directly applied. So for that, what will you do? You will say it is 1, 1, 0, 1 whole raised to n minus 1, and this can be f1 and f0. Both these are the same. If you calculate this and see, this expression and this expression are the same. What is the difference? We converted the expression which was in the form of fn minus 1 and fn minus 2 to another expression which is in the form of f1 and f0. So this can be directly calculated. Let us do a bit more on this. What do we know now? We already know the values of f1 and f0. So we need not write f1 and f0. Instead, we can directly use these values. So what will this become? This will be 1, 1, 0, 1 whole raised to n minus 1. And instead of f1 and f0, you can write 1 and 0 directly. So this is also a form of writing this. From this, what do you understand? From here, you can directly see that I'll write it here in order to make it clear, fn and fn minus 1. So from here, you actually don't want to do this computation. You just want the value of fn. And what can you see from here? From here, it is evident that the nth Fibonacci number, that is fn, is the top left element of this matrix. Whichever be this matrix, if you take the top left element of this matrix, that will directly give you fn, that is nth Fibonacci number. So what can you do? You can simply take this matrix, that is 1, 1, 0, 1 whole raised to n minus 1, Simply do this computation, and if you take the top left element, that is this element which remains after this computation, that is you have to raise it to the power of n minus 1. Whatever be the top left element, this will give you Fn, the nth Fibonacci number. This is the basic idea. The next question is, how are you going to do this matrix exponentiation? This is where the trick lies in. That is where we are going to bring it down to order of log n. So what are the steps here? The steps here are, first thing you have to define this matrix, that is M is equal to 1 1 0 1. This is the matrix you are going to use for computation. What is the next step? Step 2 is you have to compute m raised to n minus 1, where you want to find nth Fibonacci number. You have to do m power n minus 1. How are you going to do this? This is the question, because this is the most time consuming operation here. If you can bring the time for this operation down from order of n to order of log n, that means your algorithm will work in order of log n time. How can you bring this down to order of log n? In order to bring the time complexity down to order of log n, we'll use something called exponentiation by squaring. Using this method, you will be able to take it down to order of log n. So let us say you already used it. We'll explain what it is. After this, what is the third step? You have to extract the top left element of this matrix. So whatever be your matrix m power n minus 1, from this you have to extract the top left element. If you have 4 elements, out of this, whatever be the top left element, that is what you have to extract. It will be your Fn, that is nth Fibonacci number. Let us understand more about what is exponentiation by squaring. So if you want to do this exponentiation, that is m power n minus 1, what is the method to complete it in order of log n time instead of order of n? That is, if you keep doing m into m into m into m and so on, this will anyway take order of n time. How can you decrease this? The technique of exponentiation by squaring says, if you want to do, let us say m power k, this is what you want to do. If you want to do this, if k is an even number, instead of actually doing m into m into m into m so many times, instead of that, what can you do? Your m power k can be written as m power k by 2 whole raised to 2. This is another way of writing m power k. The same way, this is if k is even. Okay, if k is even, this is how you can write it. In case k is an odd number, then you can write it as m power k is equal to m into m power k minus 1 by 2 whole raised to 2. This is a way of writing what is m power k in case k is odd. So now you know that if k is even or if k is odd, that is whatever be the k value of k, from m power k by 2, you can directly get m power k. You don't need to do again m into m into m into k by 2 times. Instead, from m power k by 2, you can directly square it and find m power k. This means if you want to take m to the power n, what will be the total time taken? If you do m into m into m into and so on, it will take order of n steps. Instead, if you go like 1, 2, 4, 8, 16 like this, that is in powers of 2 if you are improving, then reaching m power k will take only order of log n steps. This is the trick here. If you are using this idea of exponentiation by squaring, then the total number of steps it will take to reach m power n is only order of log n, which means your time complexity of finding nth Fibonacci number is now order of log n. So this is the technique using which you can do this in order of log n time. And what about the space complexity here? Here space complexity is only order of 1. Why is it order of 1? Because this matrix is constant. You are not going to increase its size according to your input size. So this is a constant space, and whatever be the intermediate results you are storing, that will also be taking only constant space. So whatever is your final space complexity is order of 1, final time complexity is order of log n. So this is a very efficient way of finding nth Fibonacci number. One more thing is that if you actually want to find nth Fibonacci number and you are not so concerned of exact precision, then there is another method using which you can do it simply in order of 1. It is called Binet's formula. So Binet's formula says if you want to find this, you can find nth Fibonacci number as psi raised to n minus 1 minus psi raised to n divided by root 5. So this is a direct closed form solution for finding Fibonacci number, but this will not always give you the exact right answer. There will be slight precision issues. So ideally you should go for the algorithms that we discussed. If you want to directly find it out and you are okay with not having the right precision, then you may go with this Binet's formula as well. Here, what is the value of psi? Psi is 1 plus root 5 divided by 2. This is the value of psi. If you substitute psi here and apply this formula, psi power n minus 1 minus psi whole power n divided by root 5, you will directly get the Fibonacci number, nth Fibonacci number. So these are the methods which are better than dynamic programming for finding the nth Fibonacci number. So this is why dynamic programming, using it you can find nth Fibonacci number, but it will take time complexity of order of n and space complexity of order of n. What did we see in this lecture? In this lecture, we saw how you can take the space complexity down to order of 1. After that, what did we do? We brought this time complexity down to order of log n. We also learned about Binet's formula, which can do it in order of 1.